All right, welcome to yet another exciting night of statistics. I'm feeling a little punchy tonight, so I'm sorry up ahead of time. I like the chai, not chai tea, so that's good that you guys are learning about chai. I guess it's kai really, but to me, I keep seeing that. Anyways, let's just get right into the presentations. We got a lot to do tonight. So first I have, is it coffee?
Yes.
Awesome. And I didn't enable screen sharing. There we go. Now you should be able to try to share your screen. There we go. I heard. Great. The floor is yours.
Hi, everyone. My name is Coffee and Stu. I will be presenting on chapter 6 today, the inference for categorical data. I'll be going over chapter 6, 6.23, offshore drilling, part 1. The question is, a survey asked 827 randomly sampled registered voters, get away, in California. Do you support or do you oppose drilling for oil and natural gas off the coast of California? Or do you not know enough to say? Below is a description, the distribution of responses, separated based on whether or not the respondent graduated from college. So it's not really below, but it's right next to. First question is, what percentage of college graduates and what percent of non-graduates in this sample do not know enough to have an opinion on drilling for oil and natural gas off the coast of California? So I used the sum of the graduates, which is 438, and the population that do not know is 104, and I got to be 7%, which was divided, 23, and the non-graduates, the percentage is 33.7%. The second question was, conduct a hypothesis test to determine if the data provides strong evidence that the proportion of college graduates who do not have an issue is different than that of non-graduates. So I created a variable, let PCG and PNG represent the proportion of college graduates and non-college graduates who responded do not know. And looking at the null hypothesis and the alternative hypothesis. First, I checked for independence and the condition was satisfied because it's a random. Second, I checked the success failure condition using a pool proportion when is that P1 minus 2 equals 0. Then the calculation right now is 0.284 equal to 0. The condition is satisfied. Further expand on that, if that hypothesis, I compute the standard error right here, and then I tested the statistics. Value 0.1827. Z-score. The p-value is 0.014, which I actually took from, I hope, from the page 410 of the Open Statistics textbook, and 3.1, and we go over and 0.08, and that's the value there, and it's a double. So that's how we get this value right here. And it's a very small, so we reject the null hypothesis.
Great. Thanks so much, Coffee.
You're welcome.
Next up is Santiago. Angela, did you ever have to use Cohen's book, like Cohen's book on power analysis? like half the book is just tables like that to get those values that we just now calculate in R. So it's kind of nice to see it though still.
Yeah, I took the other approach for mine.
No, which is fine. They're both completely valid, but like it's just funny. I have this. I don't know if I could. I think in a box because I don't really need to use it very much. But like, yeah, it's a book, and there's a little book that explains the power analysis, and then like the rest of it is just tables to get the power estimates from different values from a table. Anyways, I digress. Go ahead, Santiago.
Yeah, so I had 6.47, which was about rock, paper, scissors. So it goes into some of the details about doing an analysis on whether these players chose the three options of rock, paper, or scissors randomly, or if there are certain options are favored over the others. And then this is the following table that summarizes the data. So I chose to use the chi-squared goodness of fit test, which examines all bins at the same time to determine if the options are chosen randomly. So in order for the conditions in order to use it is that there has to be independence. So each case has to be independent of all the other cases. And the sample size distribution has to be at least 5 expected cases. And so I put together a contingency table with the observed scores. And then because we expect them to be chosen equally, the expected values would be 33. So the null hypothesis is that all rock, paper, scissors outcomes are equally favored. And then the alternate hypothesis is that they are not equally favored, but there is a preference for a particular option with a significance of 0.05. So the way to do it in R is you input the outcomes in one vector. So here we have the rock, paper, scissors, and then another vector has the expected probabilities for them. So a third for each of them. And then put it into the chi-squared test with the vector with the outcomes, and then p equal to the probabilities of the outcomes, and it'll give you the p-value. So that gives you the chi-squared and the degrees of freedom and the p-value. And then using a significance p-value of 0.05, we can reject the null hypothesis since 0.023 is less than 0.05. So our test shows that there's statistically significant evidence that rock, paper, scissors outcomes are not equally favored.
Great. Thanks, Santiago. And every few semesters, a student picks this question. I love this question. Like, I just made a note to Angela that we should use this in the teaching slides, because I threw a link. I just did a quick search. There's probably better ones, but there's actually some research on this and the psychology of it. So if you want to follow up on it, it's a super interesting problem.
Yeah, because that was actually something, I mean, I didn't bring it up here, but I thought that is there actually independence between each case? Because if you're playing rock, paper, scissors, I feel like there's mind games. So like your next throw might be influenced.
That's a good question. You probably could argue that there isn't. It's the same. So if you know how counting cards works, for instance, right? So if you're playing like blackjack, is that right? Is that the game? Is that the MIT
blackjack?
So the notion of, so when you're playing a blackjack hand, the assumption is that each hand is independent. However, there's a finite number of cards, and so if you can keep track of what cards have already been played, you can sort of measure the change in probability from one hand to another. That's in essence what they're doing, is they're exploiting the fact that there's really not independence, because so anyway, I think the way casinos get around that now is they just use a lot of decks of cards. So even if you start to count, the changes, not really perceptible.
And actually, if they catch you, they throw you out. So
well, that too. Yeah, that too. All right. Good question. Good presentation. Both of you. That was good. Let me bring back my chat windows. All right. So first, before we get into content, let's talk about the data project proposal. So we'll adjust the date on Blackboard. So I'm even putting here. So push it a week. So I think it was supposed to originally be due this Sunday. Obviously, that's crazy. So let's say shoot for October 31st-ish. So, that's about 10 days or so away. If you need a few extra days, just take it. If you're going to be much more than, say, a week, reach out to us so we can kind of have a conversation. So, so first of all, about that. Also should say, we expect everyone to get perfect credit on the project proposal. So if you do not get a perfect score on the first submission, we will expect you to resubmit, because we want you to be on a good foundation for doing the presentation, right? This is going to kind of outline what you're going to do. So that's, so anyways, so do your best, and then we'll make comments, and you can revise, and, if you don't get a 5 out of 5, resubmit so we can give you more comments. So if you go to the project website, this stuff is here. There is an R Markdown file you can use. You can download this. This you don't have to be terribly verbose here, right? The goal here is to demonstrate that you have these key elements to actually do the data project, and that you've thought about it. There, I even have an example project proposal if you want to look at one, but let me just go through the question. So, you need to write a research question. So the first major thing you're going to do is actually find a data set that you want to analyze. I should have started there. So on the project page at the bottom, I give a link to a whole bunch of them. You don't have to use any of these. If you have your own, that's fine. Do really encourage you to use a public data set so we can download it, and if we need to help you, we can use it. If you're using one from your work that you can't share, that becomes a bit problematic. You should also start at this point, you're just starting the program. You might want to start creating a GitHub repo or kind of a portfolio. And so these kinds of analysis in these projects, you might want to start kind of collecting, and you may even want to pick a data set that you want to follow through in other courses. Most of our courses will have you do something like this, where you pick a data set and you're going to analyze it using the strategies or methods that you learn in that particular course. So there's a whole bunch of stuff here. You could pick, because this is sort of intro, you can also pick something that's a throwaway. 538 has a ton of great stuff. And what's kind of cool is you can kind of see how they analyzed it and then get the data, either try to replicate or try to take a slightly different tactic with the data. That's always an interesting thing to do. But yeah, there's some suggestions here, and you can chat in the general social survey, which I've used in a couple of examples already, is here. That's a pretty big data set. If you're interested in getting to bigger data sets, I'm a huge fan. If you're into education, like we are, the program of international student assessment is really great. And particularly if you're interested in education from an international perspective, that's a fantastic data set, and it's big enough, and not too big that you need to get AWS instances. You can run it on your own computer, but it's big enough to kind of present some challenges of larger data sets. There's other kind of similar ones like TIMS that I think you can get access to if that's science and mathematics, and I can't remember. Angela, chime in if you think of anyway. If you're interested in education, there's a ton of options. I only put one here. And there's multiple years, so you could do some longitude stuff. Okay, anyways, so you're going to pick a data set that you want to work with. So you're going to have a research question. Want you to identify what the statistical test you're going to do. Now, I recognize we haven't introduced all of them. So you could do a null hypothesis test using a t-test or ANOVA that we're going to talk about tonight. You could do a chi-squared like we talked about last week. But you probably know enough about regression to kind of get a sense of if you want to predict an outcome from a bunch of other variables. You could do a regression presuming the dependent variable, or what you're predicting, is quantitative. If you have a dichotomized outcome, you can use logistic regression. So we'll give some guidance if you think you're going to want to do one of those models, which I strongly encourage doing. If you pick the wrong one, we'll help you out. But so think about, I want to predict some outcome from a bunch of other variables. You're talking about some kind of regression. But identify what that is. Want to know what tell us about your data. What does each row represent? What's a case? What are the outcomes? Actually, I have that down here. Describe the method of the data collection. And in particular, related to that, is this an observational study or an experimental study? The source, so it's some kind of citation or link to the data source. And then we want to know about your response and your explanatory variables, your dependent and independent variables, and then relevant summary statistics. So just the things we talked about in chapter 2. So mean, median, standard deviation, right? If you're quantitative, contingency tables, and then have at least one visualization for each variable. And then for your final project, you're going to want to have a visualization that tries to combine multiple variables that in some way gives us a sense of the relationship. If you want to take a stab at that for the proposal, that's great. We can give you feedback now, and not absolutely required, but have some kind of visualization so we can get a sense of what your data looks like. Like I said, there's so if you look at my example one here, so you can see I have a pretty large data prep. So some of you might just have a reading a file in, but here I'm getting data from IPEDS. So IPEDS is the Integrated Post-Secondary Educational Data System. It's by the Department of Ed. It's data on all higher ed institutions, well, at least all higher ed institutions that offer Title IV funding, which is really every higher ed institution. So you can see, I want to look at what's my research question. Are SAT scores predictive of first year retention? What are each cases, represents a college or university in the United States? There are 2,281 in this particular data set. Here's where I got it from. It's an observational study. Here are the references. So my response variable is going to be first year retention, and it's numeric. My explanatory variable is median SAT score, and it is also numeric. You can see I have some relevant summary stats, and then some histograms here to kind of. So that's sort of the bare minimum of what we're looking for. And this shouldn't work yet. Okay, yeah, I didn't put the dates in. So we'll get to that soon. I need to figure out the schedule. I thought I had an example. I didn't upload it yet. So I'll upload a final project. So I don't want to over them yet. So that's the project proposal. Questions?
I have a question.
Yes,
In
please.
the final project template, it says you should have 2 independent variables, one quantitative and one qualitative. If
Where did you see that? I changed that.
It's in the template for the final project.
Okay.
So you changed that?
Yeah. So you need to have at least 2 variables, because if you're going to do a null hypothesis test or something like that, then you'll just have 2. No,
I was just wondering because I was thinking of maybe working with a time series. And
okay, sure.
So that might not have quantitative or qualitative. I mean,
yeah. This is accurate. Can you afterwards send me a link to where you saw that so I can fix it? That was a change last semester. So I tried to change it everywhere and I must have missed a spot. So I apologize. You need to have at least 2 variables, because before I didn't really want people to do null hypothesis testing, but I think it's valuable. And so the way that, just to give you a heads up, the way the final project will work is you're going to give no more than a 10-minute presentation on your results. And I'll talk about the details of that after the project proposal due date. And so I think there, with the number of students, will probably be somewhere between 6 and 8. I guess I had 8 in the fall. So there'll probably be around 8 90-minute time slots. Oh no, I said there's a maximum of 8 slots per time period. I can't remember how many I had. There'll be enough. There's usually a few during the day and a few in the evening. So if you can anyways, the point being, you're going to attend one 90-minute session, and see some of your fellow students' presentation and give yours. There'll be opportunity for peer feedback and what have you. I think it's become a really valuable component. So you can kind of see how your fellow students are analyzing data. What are some different data sets? What are the decision points you get? And I think seeing more examples is just really helpful. So if I keep scrolling down, he said, must have gone, there's the presentation slot. All right, I'll look, I'll find it. It's got to be on here. Thanks, Ray, for pointing that out. Other questions about the
Oh,
project?
I'm sorry. If you scroll right down there, it says download project template. It's that one.
Oh, it's this one.
Yeah, but it's a one for the finals, the final project. I think if you go down a little bit more.
I didn't think I uploaded the template yet. Oh, maybe it's in, is it in the rubric? No.
No, if you go to the, I sent a link where it's a fall 2021 data606.net assignments project. And you go to that and then scroll down. And it's that one. Well, maybe it changed. Oh, no, it's the one right above it. Not the one that you did click, but the one that says download project proposal template.
Oh, in this one?
Yeah. And
All
it's down at the bottom, it'll have 3 hash marks, and independent variable is when it says it right towards the bottom. Well, no, not in that form.
Not in this one?
Yeah.
In this one?
The one right above it. Yeah, and then scroll down just below dependent variable at the bottom. Yeah, right
Oh,
there.
there it is. Okay, thank you. I will fix that. Right tomorrow, but thank you. So that's not true. The statement in the template is not true. Trust
All right,
what's on the project page.
Thank you.
Yep. Other questions?
Sorry, one quick one.
Yeah.
For the sourcing, do you need MLA APA to cite the sources?
I'm less concerned, like if you just have a link to it, for your final project, work on getting it in APA if you can. I'm not going to be a stickler about that. I just want, for right now, I just want you to cite your work, and whether or not you get the details. Angela will give you feedback on she's the APA queen. She's who I go to when I need to know how to format something.
Awesome. Thank you so much.
Yeah. So I was answering for myself. I forgot. Angela might, she probably cares more than I do. And I should care more, but I don't. Other projects, not you can ask at the end too. So, let me just get started. So I'm trying to be mindful of the time here. All right, so I want to. So tonight we're going to talk about, quantitative data. So we talked about qualitative data, or we either had counts or contingency tables or proportions, things like that. So now we're going to deal with the actual quantitative data. And sort of the first example I want to talk about is data that comes from the high school and beyond survey, which is kind of a cool, talking about educational data sets. So I'm a big fan of something called NAEP, the National Assessment of Educational Progress. It's something I use for my dissertation work. I think it's an incredibly important assessment. In fact, the results just came out, I think recently. I was seeing some press. It's often referred to as the nation's report card. If you see it in sort of New York Times or Washington Post or something like that, when they write about it, they call it that. So the notion there is it's actually congressionally mandated in the late 70s that the Department of Ed in particular, and it's run by the National Center of Educational Statistics, every 2 years tries to measure, or tries to get a sense of the sort of state of education in the United States. So they assess, I think it's grades 4 and 8 in math and reading every other year. And then they cycle through other subjects. So if you're interested in science, so they might do science every 6 years and social studies every 6 years. So there's usually some other subject tests that are interspersed, but aren't necessarily every other year. High school and beyond takes students that were included in NAEP in grade 8 and follows them through high school and beyond to find out where they are, to try to kind of get a sense of the trajectory of people. So something similar, like I mentioned, PISA, which is the Program of International Student Assessment, they measure students at age 15 across the world. And it's actually done by OECD, which is a big economics organization. So even if you're interested in economics, a lot of times education becomes a pretty important variable, a predictor in lots of things that you're doing. So even if you're not in education, it's probably something you should at least be aware of. So here we're just looking at, in this case, we're looking at reading and writing scores for 200 randomly selected high school students. So what we want to do is we want to know, is there a difference between the reading and writing scores, and what's that relationship? And so great way to do it is starting with a box plot. So we can see the medians certainly look different across these two. We kind of have these, we see all the raw points as blue dots here. Interquartile ranges are, pretty close, but the medians are different. And, certainly the spread in reading seems to be a little bit larger than writing. So just kind of some quick observations that right away from a visualization kind of get a sense of, how our analysis is going to go. If we look at the data set, right, so we can see, here's each row. So each row in this data set represents one student response. And so the student has some ID, they have they have gender or sex and race and, excuse me, and SES, school type, program, et cetera, et cetera. But these are the two variables that we're going to be interested in right now. So we have a student who got a 57 in the reading and a 52 in the writing. And so we want to know, well, so the first question we want to ask is, it reading and writing scores independent of each other? And so the answer here is no, right? It's the same student. So the score on the reading is certainly dependent on the score on writing, or vice versa, right? Because you're dependent on the same individual having those two responses. So whenever, this independence question is going to come up quite a lot, sort of as a general rule of thumb, if you think about how you organize your data, right? This is kind of one way I think about it, is if I'm looking for differences, and really the difference is between two variables that I can measure across the row, right? Then they're probably dependent. Now, if I wanted to measure the difference in, so reading scores based upon, SES, well, I can't sort of do a subtraction row wise, right? So that's sort of just by the way the data is structured gives you a sense of whether or not you have independent or dependent. Why that matters, right? Because if we're dealing with, if there is dependence, right, they're not independent of one another, right? We can say that's kind of paired data, right? So in this situation, what we can do is calculate a different score, right? So we can subtract reading from writing, across for every student in this data set. And so now we just have, a single vector of values that we want to look at. And when we do this, the null hypothesis we're going to set up is the difference something other than zero, right? So our null is that the difference is zero. We want to test if it's not, so we could see the histogram. So quite frankly, this is not anything new. We talked about this a couple of weeks ago, right? When we talked about the sort of basics of null hypothesis testing, right? So we have, so that our null is that the mean is zero. And so our alternative is it's not zero. So like I said, there's nothing new here. And so we're just testing to see if the average is greater than zero. And so we can, calculate the test statistic. We find out the difference is about negative ½ a point. The standard deviation of the difference is 8.8. And so given those, we can calculate a standard error and get the p-value as shown here. It's greater than 0.05 if we're setting that as our threshold. So we would fail to reject the null hypothesis. So from here, we could do a couple other things. So you can see here is where we calculated the test statistic, right? So here we have our difference. This is our actual observed difference. And this is our null value. So in a lot of these situations, our null is going to be zero. So this just kind of gets dropped. But I like to keep it here just to remind us that's our null value. And we're not always testing the null of zero. Classic example in psychology, if you're doing anything with IQ, right, your null value is often 100, right? I want to know if my measured IQ is something different than the average IQ. So it doesn't have to be zero. I just want to remind you that, right? And so the standard error is in the denominator, right? And this gives us our test statistic, right? Which is that 0.087. And so we did a two-tailed test, right? Remember, our alternative is not equal. So we need to split our p-values above and beyond, above and below both tails, right? And that's where we get that. That's where we get this 0.38. Okay. So interpreting the p-value. So got to be careful. So it's not like, this is not the probability of us being correct, right? It's a little bit more nuanced than that. So what we're saying is the probability of obtaining a random sample of 200 students, specific, right? Has to be the same size random sample, where the average difference between the reading and writing scores is at least 0.5 in either directions, is in fact true. And that the average difference between the score is 0. So that the likelihood of that being, 0 being in there is 38%. So we can also do this through the confidence interval, nothing new here, right? So we could calculate that all out. We're using a 95% confidence interval. So we have the 1.96, and we have a confidence interval that includes 0. So remember,
Just to go back to the interpretation.
Yep.
Can you say that again? So like, if in fact the true average difference between the score is 0 is 38%. So it's saying that if in the sample, the probability of obtaining a sample where you already know that the difference is 0.545, but the population sample.
Yeah. So
zero.
Remember, with the central limit theorem, what we're saying is, the central limit theorem states that the sampling distribution is going to approximate the normal distribution.
Right.
Okay. So if we take an infinite number of samples of 200 students and measured the difference between their reading and writing scores, 95% of them are going to be in this. I think the confidence interval interpretation is a little bit easier. So we're 95% sure that the population mean is within that interval. Okay.
Right.
Which is to say that we're 38%, in this case, we're 38% sure that 0 is the true value, and that 38% is coming from the area under the tail. So we observed a value here. We're doing a two-tail test. We're going to kind of put it over there, so that the likelihood is that the mean value is either smaller and greater than the absolute value of that, is 38%.
So is this an accurate way of saying it, in that if the population mean is 0, there's a 38% chance that a random sample could have a 0.545 average difference?
No. I don't think so. Say it one more time. Just
yeah. So if the true average difference is 0, there's a 38% chance that in a random sample of 200 students, the average difference could be at 0.545. I'm kind of just flipping it around.
Yeah,
maybe that helps me. Like,
Angela, I think that's right. Yeah, I think you're right, Santiago.
Okay.
Yeah. Right. So remember, the p-value is giving us a sense of the type 1 error rate, right?
Yeah.
So it's the likelihood of. So in this case, we did not reject the null hypothesis, right? So, right. So, but there is a chance that we still, committed it. Well, we didn't reject the null hypothesis, right? So really, I think the way you're asking the question, and I don't have it calculated here, we want to go to the beta coefficient, which is that type 2 error rate. We didn't reject the null hypothesis, but what's the likelihood that the null hypothesis, we should have rejected the null hypothesis? So we have to go to that beta coefficient to get to that value. So I think that's where I got hung up. The way you're asking the question almost is like, well, what's the likelihood that we made an error not rejecting the null hypothesis? And that's what the type 2 error rate is.
Yeah, I think the way I'm interpreting it is along the lines of thinking about in what scenario I would reject it. So I'm thinking if we know that the true average difference is 0 between the scores is 0, if there were a 5% or less chance that a random sample would have 0.545 as average difference, then we could reject the
Yeah. Yep. Yeah. I greatly prefer using the confidence interval. And in
Yeah,
fact,
I just wanted to get the p-value
yeah,
too.
no, that's fair. And one of the reasons is it is so frequently misinterpreted. And so I'm trying to be very, very careful here. And I'm worried I have to go back and listen to the segment. I may have gotten it wrong. And if I did, I'll send a note or kind of do it again next week.
Yeah.
So because the p-value really just comes down to almost a dichotomized question. You're going to set some threshold, typically 0.05. And then, but what I like about the confidence intervals that we're saying this is a little bit clearer because we're 95% sure the population mean is somewhere in that interval, right? And I think that's a much cleaner interpretation. So the American Statistical Association, the American Psychological Association have all, they all have statements on p-values. And I have a reference sheet somewhere for them. And there are dedicated issues of journals to this issue.
And is it less precise though? Because you know the range, but with the other version, at least you know like what's not there. Right?
I don't know if it's less. I actually think the confidence interval is more precise because because I can get to the dichotomized question of whether or not my null value is in the interval, right? Which is all I'm going to do with the p-value.
Mm-hmm.
But it gives me a sense of the magnitude of where that true mean or difference is, right? So, and the width of the confidence interval is actually going to be proportional to the sample size, right? Because you have the square root of n in the denominator with the standard error calculation, right? So as n increases, the standard error is going to obviously decrease because that ratio changes. So, so in a lot of ways, I prefer that confidence interval so I can kind of get a sense. So I could reject the null hypothesis, but my confidence interval says that the difference is between 0.001 and 0.002. That's pretty close to zero, right? And if I just say I rejected the null hypothesis, my p is less than 0.05, I kind of lost the fact that, well, but that goes to that practical versus statistical significance, right? That's kind of why I prefer it. And anyways, in all those organizations now, if you publish in an APA journal, you have to report confidence intervals and p-values. So that's kind of how they landed on this for now. Although every so often a journal comes out and says, we won't accept p-values anymore, probably to get some publicity and people to submit articles. I don't know. But these are good questions. Does this help, Santiago?
Yeah, no, that helped. Yeah, that did help.
All right. So going back to my other, what happens if we want to know? So here we're looking at our good old friend, the SAT scores, and we want to know is there a difference by sex? Is there a difference between method? No. Okay, so Esteban, let me make it clear. I highly prefer confidence intervals, very much so. So much so that's in my dissertation, I only used confidence intervals and didn't actually report p-values. And I need to go back and reread what I wrote years ago because I had a couple of pages justifying the lack of p-values in my dissertation. I think confidence intervals are better than p-values. Now, I still use them. In fact, just the other day.
P-values are more commonly used still. I don't know if it should be, but it's still used in a lot of articles, which is why Jason is still using it. It's more if people understand, think they understand it more. It's more commonly used. It's being taught in a lot of stats courses and emphasized there. And I think maybe that's one of the reasons, but
yeah.
If you talk to Jason, confidence intervals is,
The problem is I think when we were using the other day, like when we were looking at and we'll talk about regression, and so there are like little null hypothesis tests that look at each predictor, and you want to, and so as human beings, I just want to know, is this predictor important or not? So I'm trying to get to a dichotomized answer. So using a test statistic that forces me to make a choice, do I reject or not reject, right? There's admittedly some natural tendency to want to do that. Okay, and so you can get confidence intervals from those p-values. We won't talk about it in this class. You probably hopefully get it if you take 622 or 624, I hope. But you have to go to the bootstrap to get those. They're not readily available. So people don't report them because it takes extra effort. The built-in regression modeling in R doesn't give it to you. Actually, I don't think in any stats program will give you a confidence interval for the estimates. And then, okay, so Newman's asking, can we choose any confidence level while estimating the confidence interval? Yes, absolutely. However, by convention, we have just, as sort of academics or researchers or whatever, 0.05 is where we have landed, almost universally. Now, I do see actually in some areas, like in data science, like when we get to talking about confidence, what do we want to use as predictors in a model, then I start to see people saying, well, maybe 0.1 instead of 0.05, right? And if you did that exercise from a few weeks ago where you decide whether or not you think there's a relationship, right? For me, I've done that a whole bunch of times. I always tend to land at like my personal threshold seems to be somewhere closer to 0.1 than 0.05. Okay. And so I frequently use 0.1 in particular modeling senses. If I'm doing a null hypothesis test, like we're doing tonight, it's 0.05. Now, let me tell you another example. If you go to medical research, they will often use 0.01 if you're doing sort of a medical intervention, because they want to be really sure this intervention works. And so oftentimes you'll see higher levels of confidence in those contexts. So yeah, technically, right. And one of the classic arguments against p-values is 0.05 is completely arbitrary, right? That we landed on there. It's sort of a happenstance of like the debates between Pearson and Fisher, in the middle of the last century that we ended up here. But that's where we ended up. And it seems fairly reasonable. And if you want to even learn more, I'll get references, but you'll also see references to this replication crisis, particularly in the social sciences, and what percentage, right? Which is kind of something to think about, right? If we're all using 0.05, 5% of all published research is probably wrong, if you want to state it that way. So I don't know if that's true, right? And so people are catching on to that. I don't know, but anyways, I don't want to talk about that anymore. So we're going to talk about the difference between sex, because we got some more other interesting things to do. So are they independent? Yes, right. The response for one student is independent. The males is independent of the females. And so let's look at that. So, one obvious thing is like, I can't subtract verbal and SAT to get to the question I want, right? I have to group them differently. So here I'm using the describe by function in the psych package that I like quite a lot. And I'm just subsetting out what I want to look at. So I could see, okay, I was looking at math, right? Okay, so we see for females, the mean math score is 597. And for males, it was 626. We got some box plots, superimposed the mean as a blue dot. We can see, there's a bit of a shift. Right, we can look at the distributions. If you look at this carefully, I'll just lead you in, right? We can see, well, the bump that for males seems to be up a little bit, just a tiny bit further. So some reason to think maybe there's a difference here. So if we want to do the confidence interval, we're going to do the confidence interval first on this. All right, so we have some assumptions. We have independence within groups, right? And we have independence between groups. I think we have that here. I always like to say, you do need to pay careful attention to this, because I think there is some literature where there are things like stereotype threat effect and particularly in math courses, I've seen research that suggests that girls who learn math in a classroom with only girls tend to, on average, score better than if they were in a mixed classroom. That's kind of older research. I don't know if that still holds up, but if that is true, then that suggests that there might not be independence between groups. So this is just something you need to be aware of and something you need to think about for your question. And we need to have a large enough sample size. For now, we're going to say n is 30, and we need to have minimal skewness. Again, nothing terribly new here. I think this is the same standard error that we're using. So we can calculate that out. And so we get our standard error of 1.55. Remember, the standard error is the standard deviation of the sampling distribution, right? Okay, so that's not normal. But one of the key assumptions here that we had, right, is this sample size. So what do you do if you want to compare the quality of one batch of Guinness beer to the next? Since I see Santiago, you need to try 30 Guinness beers, at least 30 Guinness beers from each batch, and rate them and decide whether or not the quality is equivalent, right? A bit of a problem, right? So getting large sample size is going to be a problem. So this leads us into my absolute hero of a statistician, Gossett, right? So you probably have heard of students t-test, but maybe you don't know where it came from. So William Gossett, encountered this problem. Literally, he was he worked for Guinness Beer Company and needed to test the quality of one batch to the next. And the sample size requirement for the central limit theorem to hold wasn't really possible. And so it's called student t-test because when he first published it, he had to publish under a pseudonym. He couldn't explain why he did this or anything. So the notion of the t-test is how do we do a null hypothesis test when we have smaller sample sizes? And so like the chi-squared, where we have a class, right? We don't have a single distribution. We actually have sort of a class of distributions. And we, again, are introducing this notion of a degrees of freedom. So in this context, for a t distribution, the degrees of freedom is simply n minus 1, our sample size minus 1. And this is what the t distribution, or here's what several t distributions look like. So let me point out first, this dashed black line is the standard normal distribution. Okay, this red line is the t distribution with 1 degrees of freedom. So what's kind of cool about the t distribution is as your degrees of freedom increases, it is going to eventually closely approximate the normal distribution. All right, so which turns out to another, right? So we have this 0.05 tradition, and now we have this tradition where we actually never report p-values from the standard normal distribution. We always report the p-values or the confidence intervals from a t distribution. Even if we have a sample size, I did a test a few semesters ago. I think once you get to like a sample size of like 400 or 500, the precision of R can't detect the difference between the two. So you could use a normal, you can use a t, you would get the same answer when you get to that size. When you get to 50, you're already like several decimal places out more than you would ever report. But for whatever reason, we only report the t distribution. So what's going on here? So remember, we're going to calculate some critical value, right? And on the normal, we've had to go, if we go 1.96 on either side of 0, that gives us 95% of the area under the curve. But look at this red t distribution with 1 degree of freedom, right? It's shorter, right? So which means I have less area here, which means I have to go further out, right? My critical value has to be further away from the center for me to reject the null hypothesis or to get to 95% of the area. So in essence, what he devised is, these distributions that have a built-in penalty for that smaller sample size. Because we have a smaller sample size, we need stronger evidence to reject the null hypothesis. Let me just pause for a second, make sure that makes sense of what's going on here. Okay. So the t-test, we kind of introduced this. So we have PT and QT. are going to be our functions to get the p-value and the critical value from the t-distribution respectively. So if we have, so if we want to use 0.05 as our critical value, and we have 10 degrees of freedom, right? We need a critical value smaller than negative 2.228 or larger than 2.228, right? Because remember, it's symmetrical. If we have p-value for critical value of 2 with 10 degrees of freedom, right? So we can see, well, that gets us 96% of the area. Now, you're typically just going to use this function called t.test in R. So it's built in. I think I might have introduced when we talked about box plots. If not, we'll get to this formula notation in R a little bit more. But in essence, right, math SAT is our dependent variable, and this is an independent variable. So this is our quantitative modeled from. We'll get into more of this when we talk about regression very, very soon. So we can see here we get, well, it tells us the mean in one group, the mean in the other group, and it's giving us the p-value and the t-statistic. This is actually using a more modern variation on the student t-test. I'm using Welch's 2-sample test. So this is why we end up with fractional degrees of freedom, but this can be a little bit more robust.
Is the process of determining the degrees of freedom kind of similar to like how you do it with the chi-square test, where it's based on the number of like rows and attributes that you're looking at, or is it more of an arbitrary thing here, where like how close?
I can't remember how Welch calculates the degrees of freedom, but by definition, using Gosset's original work, degrees of freedom in this context is simply n-1. Right.
Oh, so in this example, there were 11 samples.
These are just, no, this had nothing to do. These are just kind of like, I was just trying to show with smaller ones. I'm going here to the SAT, which had, did I say how many? Where was the SAT data set? Yeah, so there's 162.
So the degrees of freedom would be 161.
Yeah, but Welch, and I can't remember off the top of my head. Do you remember how Welch calculates the degrees of freedom? It does something, I can't remember what it does exactly, why you end up with fractional degrees of freedom. But if you just did the straight T, you would use 161 as the degrees of freedom. So it's not arbitrary. Yeah.
Got it. Thank you.
All right. So I'm trying to think what is next week's I can't remember. Yeah, linear regression. So all right, we're going to go over a little bit. I'll try to do this. And if you ask questions, I'll stay on a little bit longer. So if we have multiple groups with means, so here, right, so this worked great when we wanted to know the difference based upon sex, which we had two, in this data set, we had 2 outcomes. Just put a footnote here. I recognize that this is a problematic measure, but in education, we still, unfortunately, measure sex is just dichotomized, assigned. So really what we should do is measure, but we only have two values, right? But if we're going to measure it appropriately, we should have multiple, in which case we're going to move to ANOVA, right? So we can have, male, female, trans, whatever, whatever somebody identifies as. Right. So we have more than 2 groups. So that's where ANOVA comes in. So I like this example a little bit better. I swear I've been using this example pre-COVID, but it has become even more relevant of late. It's a kind of a nice little, because it's small and you can do a lot of these calculations by hand if you need it. But what we wanted to know is the difference in the bacteria, how good washing your hand is with just water, regular soap, antibacterial soap, and antibacterial spray. A couple of interesting things about this data set. Each was replicated 8 times. So we have 8 outcomes for each of these 4 types of hand washing, and they were all randomly assigned, right? So in this example, we're going to do ANOVA, and we can actually make causal inferences from this one because we randomize, but that's only because it's randomized. And I just like to show that, right? So the way ANOVA is working, right, is what we're testing here, or the null hypothesis for ANOVA, is that the mean is the same for all of the groups. Okay, that's key, right? And this in the null hypothesis over here, we're saying the mean outcome of the math SAT scores is the same based on sex. Here we're saying the mean bacterial count is the same for all of the groups. Okay, so then the alternative hypothesis is that they are not the same. And what you need to be careful here is if you end up rejecting the null hypothesis, it doesn't say anything about which group is different, right? Although when we look at the descriptives right away, we're going to be suspicious, right? We're going to say, well, that alcohol spray certainly resulted in far fewer bacteria than the other three methods, right? So when we do the ANOVA, we're not saying, all we're saying is these four means are the same. That's what we're testing. We'll get to the other part in a moment. Okay. So let's do some descriptive stats so we can see, right? So alcohol spray, the mean is 37.5 and 92. And we could get the mean of the variance, right? So, so the variance is remember, is the standard deviation squared. So a couple of other stats that I'm going to use is the mean of the variance across the groups, right? And then just the variance for the bacteria counts, right? So this is kind of, right, this is the mean variance across the groups. And this is the mean variance within the groups, right? When we pulled it all together. All right, so there's a bunch of components here, right? So here's our null hypothesis. We're saying mean of group 1 is equal to mean of group 2, et cetera, et cetera. So we're going to need different pieces here, right? This is called analysis of variance. So we're going to really look at the variance estimates here to determine whether or not the means are different. So we can define the between sums of squares, right? So let's look at the formula here. So we're summing across the product, right, of the group mean. So K is the group. So this K is going to be alcohol spray, and then it's the mean. What's the other? Water, et cetera, right? So we have 4 of them. So this is going to sum across, there'll be 4. In our example, there'll be 4 things to kind of sum here. So we're taking the mean of the group minus the grand mean, right? So this is the mean back to, so first, if we have the alcohol spray, so we're taking the mean for alcohol spray minus the mean of the bacteria count overall. Square it times the N for that group. So in this case, it's 8. And I fixed it that way. So that goes away, right? So you see how this is, we're kind of getting a variance estimate, right? So the variance, right? If you think about when we talked about variance as a descriptive stat, how did we get the variance? We took each value and subtracted the mean and then squared it and summed it. That gives us the variance for a measure. So this is just another kind of measure, but this is the variance across the means for each group. So we call that the sums of squared between, right? Because we're summing, we have some squaring. Then we have this kind of double summation. So we're taking within each group, we're kind of calculating the variance within each group and then summing that across all the groups, right? Does that make sense? So we have the alcohol spray. We're taking each observation from the alcohol spray, subtracting the mean of the alcohol spray, squaring it, summing that up, and then we're going to do that for all the other groups. So that gives us the sums of squared within. So within each group, we have some variance estimates. So we have between, which is really just, you can think of as the variance of the means, and this is the variance within each of the groups. We also have 2 sets of degrees of freedom here, right? So we have the between, right, which is K minus 1, which is the number of groups we have. So in our example here, our degrees of freedom between is going to be 3 because we have 4 groups. So there's 3 degrees of freedom. The degrees of freedom within is going to be the number of groups we have times n minus 1. So within each group, right? And this is kind of key for this example. So if you're actually going to calculate ANOVA by hand, having equal group sizes makes this a lot easier. It becomes really complicated. And so we're just going to rely on R because each group had exactly 8 observations, right? So if each group has 8 minus 1 or 7, we have 7 degrees of freedom essentially within each group, and we have 4 groups. So our within is going to be 7 times 4 is 28. Am I doing that right? I'm not good at arithmetic in my head in front of an audience. Okay. Hopefully so far so good. Then we have.
What happens if they're not even?
Okay. Don't. I was trying to get you to not ask me. Different software handles it a little bit different. So again, when we run the ANOVA in R, we'll end up with fractional degrees of freedom. I can't say for sure, but I think what it does is you have to go through, and I think you add the degrees of freedom for each one. So you would say, instead of just multiplying this by groups, right? I think that tends to be what it does. So if I had 8, 7, 7, 8, right? 2, 8, and 2, 7. So I'd probably have 14 plus, what did I say? 7, 6, so 14 plus 12. So maybe 26 degrees of freedom, I think might be where you end up. But that's kind of roughly what happens. That's not exactly what happens. You kind of have to kind of do some averaging across. The software will handle that. If you're super interested, I can get in the details. I have a odd relationship with the ANOVAs because next week we're going to talk about regression, and ANOVAs are a special case of regression. So typically when I encounter these problems, I run them as a regression model instead of an ANOVA problem. But there are a few instances where the ANOVA becomes a little bit more straightforward to interpret if you're testing the mean across a bunch of groups. But you could technically run this as a regression and get to the same answer. But I need to teach ANOVA because we need ANOVA to look at some model fit statistics later on. So it's worth knowing this. Okay, so now we have 2 metrics, like 2 kind of, you can think of them almost as parts of a test statistic. We have the mean square between, right, which is the sum square between divided by the degrees of freedom between. And so we have then a mean square within, which is the sum squared within divided by the degrees of freedom within. Sometimes these are called mean squared treatment and mean squared error, right? And I think I have a visualization that will kind of get that come through in just a moment. So in an ANOVA, really what we're going to look at is that we're interested in this ratio between these 2 mean squares, right? So if we're assuming the washing method has the same variance, then we can pull them together, right? And sort of compare that with the pooled variance with the overall variance. So remember on a slide before, I had calculated the variance across here and I took the mean of it, right? Which is this 1410 value here. So that's called, so that's the average variance across all groups. Okay, so if we look at the ratio of these, right? So if the mean squared treatment, right, estimates the total variance if the null hypothesis is true, right? And if it's larger than the pooled variance, then the null hypothesis is false. For the mean squared error, right, it should estimate the pooled variance, whether it's true or not, right? And so if the null hypothesis is true and both close to that and close to the mean square treatment, the mean square treatment is close to this. So what we're going to do is just take the ratio of these things. So if the null hypothesis is true, the ratio of these 2 things should be close to 1, meaning, and actually I have a picture, I think that might help, right? So as the ratio grows, gets larger, then we have more evidence to reject the null hypothesis. Now, a couple things, right? These are essentially variances, right? Because remember, the sums of squared has to be positive because we're squaring everything. So if we have any negative values, we square them, it becomes positive. Of course, degrees of freedom is always positive. So both these values are positive. So like the chi-squared, when we take the ratio of these things, they're going to be bounded by 0. We can't have a value less than 0. So again, we're gonna do one tail test. So what is this ratio? Well, this is called the F statistic and the F distribution.
Excuse me, Professor.
Yep.
I was thinking that the degrees of freedom within groups is n minus k. But like this formula, like within
Within?
groups degree, yeah, I thought it's n minus k. That if you do the math, that's not n minus k.
Nope. So we have 4 groups. We have 8 observations per group. So you can think of the degrees of freedom within each group is n minus 1. So it would be 7. And then you got to multiply it by how many groups we have. Because we have 4 groups. We got to consider the degrees of freedom in all our groups, right? Now on a t-test, right, we would just take n minus 1. But here, I should clarify, n here is the n within each group. Actually, I should probably have a subscript here.
You do that, you probably want a summation of k.
Yeah.
Yeah, I understand. I mean, it's just that prior one way ANOVAs that have done usually is n minus k for within groups. So I don't know. It's different.
Let me work through the example. I'll come back to you. I don't know who was speaking at that time. Sorry. All right. Okay, here we go. All right. So this gets, we just want to look if it's larger than just due chance, right? And so that ratio is called the F statistic. And we have a couple of pieces here. My colleague wrote this great little app here, so we can go in here and actually look at all of the F distribution. So in our example, we had, so what did I say? So we have 4. So the numerator degrees of freedom is 4. So I can make that 4. No, 3. Is it 3 or 4? It's 3. 3. I can do that. Right. And then I said we have, so I have, oops. So we have 4 times 8 minus 1 should be 27 or 20.
8.
28. Thank you. All right. So if we, this is what the F distribution is truncated here. Again, like all of our distributions, the area under this curve is 1. So we can interpret areas under it as probabilities. So we need an F, in order to have a 0.05 threshold, right, which is what we're typically going to use, we need our F statistic, or that ratio, to be larger than 2.95-ish, right? At exactly 2.946669, that's where we get 5% of the area under the tail, right? And that's what we're looking for to reject the null hypothesis. So, all right, and so I plotted it here too, using my distribution function. Okay, so here's how ANOVA results are often presented. So you tend to have what's called an ANOVA table. And so what we want is the between group, which is sort of the treatment, and the within group, which is the error, and then the total, right? So this is not new. This is the same variance estimate essentially we had from chapter 2. Okay. So, and then we have our degrees of freedom listed here, right? And then here for the total degrees of freedom. Then we have our mean squared, our F statistic, and then a p-value, which is the area to the right. So these are all the pieces that we need to calculate. I actually pull up this slide all the time when I go read an ANOVA summary to remember what the different components are. So here are the steps if we want to calculate it by hand, or well, with R, step by step. So we're going to need a grand mean. Here's our total N. Here's our K, our number of groups. And here's our sums of squared total. Okay. Then we have our between groups. So we have 3 degrees of freedom. Here's our sums of squared. So I'm taking the N, right? I'm taking each mean minus the grand mean, squaring it, getting the total. And then the mean squared between is the ratio. If I'm looking at the within groups, right? So there's my degrees of freedom within, which is 28. The sums of squared within, which is the sums of square. Okay, I'm doing a little cheat here. You go back here, right? So what's, what is this? So the sum of these two sums of squares has to equal these. And so since this is easy to calculate, right? And I have the total, right? Because that's also easy to calculate. Well, to get the within, I can just take the total minus the between as a shortcut. And so then I have the mean squared within, right? And so if we do that, take the ratio, I end up with the F statistic of roughly, or the p-value for it. So the F statistic is 7.06, right? If we looked over here, remember we were looking for something greater than 2.9. Right, and so I'm going to use the PF function. So again, remember the P function is going to give you the area under the F distribution to the left, which is why I have 1 minus, and I have to pass in my 2 sets of degrees of freedom, right? And we often write it this way. So we have 3 and 28. So the p-value is very small, so I would reject the null hypothesis. Okay, and I plotted here so we could see it using this function. I swear that there is something shaded here. You just can't see it. Okay. We're getting close, and I can review this next week if there are further questions. All right. So some assumptions, right? So we have the outlier issue, as we always do. We need similar spreads. Skewness can be problematic, and if you have any of those, re-expressing. We'll just gloss over some of that for now. The independence assumption, right, kind of similar, right, to the assumptions in other tests. All right. But in ANOVA, because we're pulling the variances, right, this equal variance assumption can be key, right? Sometimes it's referred to the similar spread. So we're kind of expecting the variances within each of the groups to be roughly equal. And if there's large deviations from that could be problematic and will make the results a little less robust. So in R, though, there's a function called AOV for ANOVA, right? We're using the kind of the same formula notation, bacteria counts by methods, and I get the summary. And you can see here we get that ANOVA table that we calculated by hand. Okay, so let's talk a little bit. We got 43. Okay, I think I can wrap this up within 5 minutes. All right, so what do you do next, right? So the null hypothesis was that all the means are the same. We reject the null hypothesis, so the means are not the same. Does that mean we can say the bacterial spray is better than everything else? No, not yet. We want to do some paired comparisons, right? But one of the problems with that is every time we do a paired comparison, we increase our likelihood of committing a type 1 error. Okay, so if you want to do multiple comparisons, we need to do some kind of adjustment to our type 1 error rate. So the most conservative and classic way of doing it is something called the Bonferroni. So in this case, if we want to do 3 pair tests, right, we saw the descriptives. We really just want to say we want to compare the bacterial spray to each of the other ones and say is bacterial. So we're going to do basically 3 paired null hypothesis tests. And we want to do a 95%, we want to be 95% sure in our type 1 error rate. So what we're going to do is take our error, or our 0.05 that we're allowed to do, and divide it across the 3 compared tests, right? So if 0.05 was our chance, so instead of doing a 95% confidence interval, we're going to do a 98.3% confidence interval, so that our overall type 1 error rate is still 5%. Okay, does that make sense? So we're just splitting the error across those multiple tests. And so, and you can kind of see this here in this visualization. So this is a great way of kind of summarize. I like the box plot, but what I've done is superimposed confidence intervals for each of the groups. So, so I'm calculating critical value. So here, if I were just to plot this, right? So in this case, I'm looking for, if I have non-overlapping confidence intervals, is typically how you interpret this, then I would say that there's a difference. So without any adjustment, right, I would say alcohol spray is different than the other 3, but these 3 are the same. But really what I want to do is just 3 pair tests, right? So here you could see in my critical value, I'm dividing by 3. So, so I have, overall at 95% confidence interval for doing 3 pair tests. So you see my confidence intervals, how they got a little bit bigger. right? But there's actually 6 pair tests I could do here. So if I want to compare everything to everything else, right, really, you know, I need to go even further. And so if I go that far, right, then I will say, well, really the alcohol spray is different than water. That's really all I can say. Everything else is kind of the same if I'm comparing everything to everything else. So these are just some things you need to think about when, you know, once you get that difference, where are the differences and how do I do that? Okay. Just to kind of, so I have this is sort of a prototype of a little shiny app I've been working on, because I will admit I struggle at times with the Novus. Do not feel, if you feel overwhelmed, ask questions in Slack. You can ask them tonight. In fact, maybe I should have Angela chime in, because I think she might, you probably do a Nova more than I do. Did you do a lot of Novus in your dissertation? I thought you did. Oh, no. Okay. So if we think about, if we, you know, and actually this is going to come up too in the next few weeks. Let's think about when we're squaring stuff, what's going on, right? When we essentially have a square or a rectangle, right? So we can kind of conceive these mean squares as areas, or as squares, or in this case, squares. Okay. So what I've done here is I've simulated a data with 3 groups with 10 observations per group, and I can adjust the means for each group. And I fixed the standard deviation at 3, right? Because I need to have equal variance. So I only give you 1. You know, the variance within each group is going to be set as 3, and I'm just randomly sampling stuff. So here, what I have is this contrast coefficient. So, well, let me explain what happened here. So first, for group A, which is this group here, this red one, right? I randomly selected 10 values where the mean was 1 and the standard deviation was 3. So these little red circles, those are my observations. This red dot is the mean for group A, right? And so here's group B that has a mean simulated data where that the mean should be around 2. And then here's my third group where the mean should be around 3, right? And you can see the raw data there.
And all groups have the same number of standard deviations, or the?
Yeah, it's always 3. I only give you one choice, right? Equal variance. That was that equal variance assumption. So I fixed it. Okay. Now, what I did here, and I can't take credit, this is my dissertation advisor did this. I create what's called a contrast coefficient, which is really just a fancy way of saying I created a new measure here where the mean of the means is standardized. So I essentially calculated a z-score of the means. So you could see that middle group is pretty close to 0. And we get, so group A is here and group B. So that's just to allow me to position on the x-axis, you know, where I want to draw these vertical lines. And then the y-axis is just my dependent variable, right? So that's defined by these metrics here, the means and stuff. Okay. So first thing is, if we think about the variance within each group, right? So what are we doing? So we're taking like this point minus this squared, this point minus that point squared, right? So if I'm squaring all that, that's a square, right? And so that value is represented by the variance of this for group A is represented by this rectangle, or this square, this red square, right? Such that the area in this square is equal to the variance for group A. Okay. Then I did that for green, right? Took each value. And so this green box is representative of the variance for group B. And then I have group C, which is this blue box. So far, so good, right? If you want to go back to the formula, right? For each variance, where is it? Well, it's just this part of each group, right? So each of those squares I was talking about is just this part. If we didn't sum it across all of them. Okay, ooh, I'm in a different tab. Where am I? Okay. Right. So if we think about the mean squared total, well, what I did is I calculated, right? And so that's this green square, right? And then this yellow square is that mean squared between. So so this yellow one in the middle, right, is the average of these 4 squares, right? If I take the area of those 4 squares and average them, I get this yellow square, and I just positioned it directly in the middle of the plot. So it's centered on 0, right? So here's my grand mean, right? That's this horizontal line, okay? And so that's the grand mean, and so that's that variance. So then if I take the total variance, which is the across the groups, right, I get this green square, right? So in essence, the F statistic, right, if you think about these as now areas, is simply the ratio of the area of these 2 squares. Okay, and you can kind of see that. So if I take, like, say, group C and start to make the mean bigger, and sometimes you get bad resamples. So let me go a little bit further. Okay, let's go extreme.
Sorry, can you just pause on one of them for a second?
Yeah.
So okay, the red square is one group, green square is one group.
Group A,
And
that I
then-
had a mean of 1.
Right.
Then the green one has a mean of 2, so it's only a little bit bigger than this one, right?
And because they're all standardized for the z-score, that's why the yellow one is right in the middle, because it's saying,
yeah. So I'm gonna put the yellow square centered. So the yellow one, I just center the square on the contrast coefficient of 0 and the grand mean. So
and then the area, like what is that's based off of the F statistic?
so this area is the mean squared between. I think I have that right. Mean squared between, or mean squared with. It's no, I'm sorry, it's the mean square treatment. Okay, this green square is the error.
Okay.
Okay, so and so as that ratio gets bigger, so here now we have an F statistic of 16.5, right? So you could see that up there the whole time, right? And what's happening, right, is so we're looking at the average ratio of the variances within each of these groups compared to the total variance. And as this mean gets bigger, right, it's causing this green, that ratio to get, actually, I think I said that backwards. The green is the treatment. This is the error, right? And so we're accounting for, we're getting that ratio bigger. And as we keep going further, right, it's going to kind of keep making that square staying smaller, but the green square is getting bigger. So it's going to make that F statistic, that ratio of the green to the yellow, really, really big. Where if I go back to, if I make it 2, right, see these 2 squares are almost overlap, right? So the ratio of the area of those 2 squares is now, as we get closer to 1, remember, then we're saying we're just estimating the pooled variance to those mean squared components. Yeah, I could see, Santiago, thank you for having your screen on, because this is the kind of feedback, nonverbal feedback I need.
Yeah, I think there's a lot going. I mean, I feel like I was almost getting it, but
Yeah.
there's just like a lot going on. And like I feel like if it's easier to like, I kind of get what it's going for, but I'm not quite there yet. It's like kind of like I see how there's a relationship across everything, but it's just not clicking.
Yeah, that's fair. And this may not be helpful for lots of folks. For me, why I was going down this path, and like I said, this is a prototype, and I may just abandon this way of thinking. So that's the feedback you give in the 1-minute papers, please do. But what I'm thinking about here is I have these, when I see this squaring, right? To me, this is like the edge, one edge of the, this is, well, in this case of a squaring, this is a rectangle, I mean, a square, and the length of each edge is the mean of K minus the grand mean, right? And so I started drawing that. So the key is the contrast coefficient, which confused me for a long time when I first saw this, but this is a rescaling of this, using the means, so that you kind of have, because I got to make it a square somehow, right? And by using the contrast coefficient, I'm just drawing these here. So, this is a vertical line. And this is kind of the standard score for the mean of group A, using the three groups going across, right?
So the contrast coefficient is where you place it.
Mhm.
Because I think it's helpful to see like the squares as an area. Like that helps
Yeah.
me. Like I like seeing like, okay, well the mean squared represents the area and it represents a literal square.
Mhm.
So I get that part. That's what you're saying. Yeah. It's like,
Yeah.
how do they relate to each other? And then where do you place them? And then the
Yeah.
standard error in there.
So I probably should show the calculation of the contrast coefficient, but it's I can't remember off the top of my head, but it's standardized so that if I take the mean of the three groups, I want it to be 0. So it's essentially a z-score using just the means of the groups.
So what if you had two groups? Maybe that'd be easier.
Yeah, let's
Or
I
like
can
how
do
does that
that.
look?
And let me, right, so they're equidistant.
Mhm.
And with two groups, right?
So what's the blue dot? Is that that's the
Grand
mean of
mean.
the two? The grand.
It's the
Okay,
grand
yeah.
mean.
So this makes, yeah, okay.
That's the grand mean. If I took all the values together, right, and calculated the mean, that's this blue dot and that's this horizontal line. So it's 0, right? So the key advantage, because the contrast coefficient tends to be is a rescaling, a standard scaling of this, then I have this unit line that always goes through all three means. The means will have to lie on this point because of the way I calculated it.
And the slope is,
Well, it's
or is there nothing?
I wouldn't interpret the slope. It well, it could be one. I don't know.
It certainly looks like it's 1.
Yeah, I think it might be a unit line, but I can't say for sure. That's a good question. But the key is all the means have to lie on that line, right? Because they're just kind of rescalings of the same metric, right? And this one went high. Oh, the other thing I did here, yeah, I think it is 1. It is absolutely 1 because now I remember what I did. This is ggplot. So I used the chord equal. If you haven't encountered that, you can do plus COORD_equal, and that ensures that the distance in the x is the same in the y. It makes it a square. If that makes sense. So the distance, or if you don't do if I didn't do that, this plot would be stretched wide and they wouldn't be rectangles anymore. But I want them to stay rectangles, so that's why I use chord equal. So yes, it is the unit line. So the slope of this is 1. It's always 1. I just had to talk that through myself.
And
let's go to 4 groups because maybe, especially if I make, those two the same, and then really when you make one of them bigger, right? So you can see, right? So this, again, this yellow square is just the average of the area of the 4 individual squares. And then this is the total variance. So that's like mean squared. Oh, damn it. I keep getting this back.
sorry, do you mind just going back to the two?
So this is the mean squared within, right?
Yeah.
So the mean squared within is the average across all of them. And then this is the mean squared treatment or between, right? So because now I have this group that's kind of pulling away from the other 3, right? That's going to make this green rectangle bigger because I'm introducing kind of more variance there.
If you box plotted each of the groups, would the means of the box plot, would they kind of line up similar to what they look like on this diagram? I'm trying to put this in context.
No, not quite, because when you do the box plot as I did here, right? They're just going to be equal distance. So by using the contrast, I'm actually trying to get a numeric value for the y-axis, so that the distance from the red to the green to the blue actually has meaning here, right? So this is sort of a, the difference in the means as we go across, and so then we have this big gap where group D is way out here, right? So these three are kind of close together.
And it's
right?
how close they are to the yellow square that makes that
Well,
significant?
as close to one another,
Or to
and they're
one another?
below 0, so they're below the grand mean. But then we have this one here that's kind of got this bigger distance. So we could play around with this some more. And so if we had 2 at 1, right? So here we have 2 groups that are, way above the grand mean, and 2 groups that are well below the grand mean, right? And I got a bad sample there. So so now you can see this red one has a slightly smaller, but roughly equal variance across, again, the average. But then as we go across, they get all bigger. But if I make these now, like if I actually make them all the same, right? So there's some sampling variance here, but you could see the green and the yellow are actually, what I need to do is I should have check boxes so I could turn on and off each individual square to build it up. I think that might help too, because I'm just showing everything all at once. But the key is I want to turn off the group squares, because the yellow and the green, which is kind of a little bit hard to see here, are almost the same size, right? And that's that F statistic, is that ratio of those 2 areas. But I can pick any of these groups and go higher, right? You can see this is group C that's out here. There's yeah, this is using an actual data set. I don't want to go into that because I'd have to explain where it came from. I'll just stick with the simulated data. All right, why don't we put a pin in this for now? If this wasn't helpful, I'm sorry. But you asked some good questions, and I got some work to do on. I'm just trying to find better ways to explain this. If you're doing ANOVA, this is the slide you want to have, I think. In particular, because when you look at an ANOVA results table, the values are going to be presented in this format, and this gives you the formulas of where all those values came from.
Could we look at our Shiny app? I feel like I'm so close to getting it, and I just want to play with it.
Yeah. Yes, I'll upload it and I'll put a link. I'll let you know. I'll upload, because it's not on GitHub right now, but I can put it there so you can play with it.
Okay, thanks.
I know we're beating a dead horse here. Could I ask you to use the words between and within as it relates to the Shiny app now? Looking back at the Shiny app, visually.
Yeah, I wish I could get these side by side. So, did I lose Angela? So I got to look at it this way. So the between group, right? So we're taking the group mean minus the grand mean and averaging it. So that's going to be this yellow square. The within group is taking each observation minus the group mean, summing it across the groups, and then all the way across. That's going to be this green square.
And so could you make a sentence how does that relate to the hand washing with the alcohol and stuff, as it relates to the visualization?
So this is well, what we could say is in this here, I think I did 4 groups. So here we have, we could have the 4 types of washing hands. Okay. we have the means of the bacterial count across each one. So then we have the variance for each group. And we have the variance, we have the variance between the groups, which is this yellow square. And then the within group is this green square. So as the ratio, right? So we're comparing variances. So we're comparing the average variance of all the group, right, to the total variance, right? So this, think about this green square, right? Because now we look at what this formula is doing. So we're taking, so I'm going to start here. I'm going to take this value minus this value squared, plus this value minus this value squared, plus this value minus this value squared, right? Then I'm going to go to this group, this value minus this value squared, plus this value minus this value, right? All the way through. So, you know, as that get, you know, because there's a difference here and we're spread out more, right? That is going to, you know, make this square bigger than the average across the groups. So as that ratio increases, as it gets further away from 1, right, we're going to use the F distribution to get that p-value. So as that ratio gets larger, we're increasing the evidence that the means are different. But we're not comparing the means directly. I mean, the means are in there because, you know, they're part of the calculation, right? So, right. So the between group, right? So I'm taking this value minus the grand mean, this value minus the grand mean all the way across and summing that, right? So the mean to the means of each group to the grand mean as a ratio of every value to its group mean across, you know, across all the groups. So when we get this, so if I bring this back down to 1, right? So now the reason why the squares are, oh boy, this can be hard. Maybe 3 groups isn't. This one's close. Yeah, we still have a small f value. So here, right? So I'm taking, so I'm calculating to get that green square, I'm taking this value. I'm sorry, to get this yellow square, I'm taking this value minus the grand mean, this value minus that squared, this value minus the grand mean, that value minus the grand. So that's all pretty tight, right? These are all, that's pretty small. Then I'm taking this value minus this all the way through, which is going to give me something that's going to be close to as if they were all kind of grouped together. So that's why that ratio is there. So then that area is also going to be kind of small. So when I take the ratio of it, it's going to be pretty close to 1. But as the group mean gets larger, right? So I'm looking at this one here in particular, right? Right. And this is going to come up next week when we talk about regression, like this notion of why we square things. But think about like, so now so I'm taking this value minus the grand mean and squaring it, right? So as it gets further apart, it's not a linear increase, it's a geometric increase in that value that's going into this summation, right? And so that's what's going to make that value, that's what's going to make the numerator bigger, right? As I calculate, as I have something that gets further away from the grand mean, I'm taking that difference and squaring it. And that's going into the numerator of my F statistic value, right? And that's how we're determining that, oh, there is a mean that's kind of different than the rest of the means.
Sorry, I know.
No, it's fine.
Why is the whole green in this as it is now? Why is the whole big green thing called within groups? What does the word within mean?
Angela, are you there? Do you know? Because sometimes they're called treatment, an error, and the treatment error makes more sense to me when I use. So
within groups, if you look at the formula, it's because you're subtracting each individual observation from the group, from its own group mean, right? So that's why it's within groups. So you're looking into the differences within the group in which they belong, right? Whereas the between group, you're looking at the difference between that group minus the grand mean.
Yeah. So in using this area example, right? So I have the variance for each of my groups, and the yellow is, am I getting the right one? No, this, I think ends up being the green square.
So I think the between group one is the green square, is the bigger
Yeah.
square, right?
Yep.
And the within group one is the one in the middle, the orange one or the yellow one.
Yeah. Right, because I'm taking these values and squaring them, so it's making it larger.
So I don't know, I didn't see it close enough, but I believe when you made one group bigger, Jason, the green group, the green box became a lot bigger, right? But when it was all, but the yellow box inside didn't grow significantly bigger because it's within group.
Yeah, because it's fixed to the, okay, so actually, you know what, you're right. Right, of course. So if I think if I increase the standard deviation, that should make the yellow square bigger.
Yep.
Because now I'm changing the variance within each group. Right, so if I go all the way down to 1, oh yes, that makes. So that's also right. So if I have a standard deviation that's so large, right? So the difference between, I have 6-point difference, but my standard deviation is 7, right? So now I'm getting close to, you know, I guess I have to make it a little bit bigger. Now my F statistic isn't significant, but I did make that group so much bigger. Okay. All right. Well, I got some work to do. I think a couple of, so this was helpful for me. I'm sorry if it wasn't entirely helpful for everyone else. I try new things sometimes, and sometimes they work, sometimes they don't. So
I think it was helpful, even though I didn't have that like eureka type moment. It still was helpful.
Well, if it's any consolation, here, so I'm gonna put the 1-minute paper in the chat. I think people dropped off, and which is completely fine. But for those who are still here, so the other thing, graphical, no, I can't, graphical analysis of variance.
One way to kind of get the within, and one way I kind of think about it is it's kind of like factoring. You know, when you do like ggplot and you factor out the group, it's kind of like that, because you're just taking that single group. And then when you graph it, you're comparing it to the other groups. So it's kind of similar to that, except you're taking away, you know, every element of that groups from that single group's mean.
So this is based upon work of my advisor, and he labels it. And I was trying to build it in a build up way. So maybe read this. Maybe I need to reread this paper. At least the one way ANOVA. 2-way ANOVA gets crazy because then you have 3D plots. And I'll show that only in terms of interaction effects in 3 weeks, I think. All right. Well, oh, one other thing I cannot believe. Okay. I'll put this in the Slack too. On November 30th, I'm going to give a talk during the day on Shiny, which is an R package. That's what I use to create this thing. If you're interested, it's not like part of the course. It's just kind of, it's I'm cross posting it with our Albany R user group, but it's going to be an online virtual Zoom workshop. So I put the link to that. You need RSVP to get the Zoom link. And then last but not least, I have this thing sitting here the whole time. I'm going to open myself. I think I earned it tonight. And I have myself a Guinness beer and salute to the student t-test and gossip. So next time you have a Guinness, think that you have stats to thank for it. All right. Should we call it a night? Yeah, thanks. See everybody next week.
Thanks. Good night.
Thank you. Good night.